Hello and welcome to this course on discrete mathematics, and we are still dealing with algorithms. In the previous part 1 we have seen some basic algorithms, right? So today I am going to introduce some examples for those basic algorithms. Let's begin with the basic bubble sort algorithms. We have seen examples for linear search, binary search, but we didn't see the examples for the bubble sort. Well, if you recall the bubble sort algorithm, it has some iterations as well. Let's go through quickly some of the ways in which we can do the iteration process. Say for example, let's begin with having this array of elements with 4, 5, 1, say 4, 2, 8, and here you want to sort by means of this ascending order. So what is the first step that has to be taken in the first pass? In other words, it's the first iteration. In the first iteration, let's see what are supposed to be done. So initially it compares the two elements. So what happens here is the first part, it's going to be interchanged. 5 and 1 has to be interchanged initially, and then 5 and 4 will be interchanged initially after that. For let's say 5, 1, 5, 4, 2, 8, then 1, 4, 5, 2, 8, then 1, 4, 2, 5, 8. So this is kind of the way in which it would be sorted at the first iteration. So if you recall what is happening here, this is where the swapping takes place. Again the swapping takes place here, and that's the way it's happening here. The swapping takes place and the swapping takes place. In fact, the last one does not happen, the swapping. So that's your first iteration, and your second iteration starts with this one, 1, 4, 2, 5, 8. That's where you are going to have your second iteration. And in the second iteration again we can see initially 1 and 4 there is no swap, but for 4 and 2 you can expect a swap. So you have 1, 4, 2, 5, 8. Initially there is no swap for the first part, and then here you have a swap from 4 and 2. So let's say 1, 2, 4, 5, 8 is there, and again if you look at 5 and 4 there is no swap at this point. So then you have 1, 2, 4, 5, 8. So is there any other swaps that you can expect? And in fact at this point there is no more swap is needed. So since there is no more swap is needed at this point, again 4 and 5 and 8 is not swapped, we go for the third iteration where we start with 1, 2, 4, 5, 8, and here initially there is no swap in this position. So 1, 2 there is no swap, and again for 2 and 4 there is no swap. So you write down the same thing again. If you go on the steps, you will notice that you are not going to swap for 4 and 5 as well, and you are not going to swap for 5 and 8. So there is no swap altogether, so which means that there is no more changes needed for to be done. So that's the simple bubble sort methods that we have seen here. So with this bubble sort methods, let's go on and see some more information about the insertion sort runtime. As far as the insertion sort is concerned, this is the basic idea behind the insertion sort. The algorithm is given to us, and you are expected to do it this way. So as we can see here, the insertion sort, we pick up a key element there and compare it with the element ahead of it and put the key in the right place. So if it is needed, we have to interchange. So say for example, let's look at this example again, similar to the one we have seen earlier, say 5 6 or 5 1 6 2 4 3. If this is given to us, and initially when you compare say for example 5 and 1, we know that 5 is greater than 1. So then you are going to expect there is a change. 5 has nothing before it, but after 5 you have 1. 1 is compared with 5, and when you compare 1 with 5 and is inserted before, you are going to compare the 1 with 5 and you are going to insert before that. So 1 is inserted before 5. So that is what happens: 1 5 6 2 4 3 there, and you know that 6 is greater than 5, and yes, 6 is greater than 5 and also 1. Since 6 is greater than 5 and 1, we do not have to perform any task at this point, but we know that 2 is smaller than 6 and 5, right? 2 is smaller than 6 and 5, but greater than 1. So it is inserted after 1. So you are going to take 2 and you are going to insert after 1. That is why it is kind of an insertion sort. So that takes us to this part: 1 2 5 6 4 and 3. And again you can do the same thing, like 5 and 6 are greater than 4. So 4 is expected to be inserted over this part. So it takes 1 2 4 5 6 and 3. And what happens now? Again 3 has to be inserted over here. So 1 2 3 4 5 6. That is how it goes on, this whole problem. I hope you got this idea. Yes, the outer loop of runs n minus 1 time. Inner loop goes for this worst case scenario, would be like I at 1, and for the loop runs a lot of times there. So if I is 1, the inner loop runs 1 time, and k goes from 0 to 0 for the first iteration. Yes, it goes from one iteration to another iteration, 1 time on the second, and up to n minus 2 iterations. So it goes on like the total computation here is n minus 1 n minus 2 by 2. So it is like as if n square times. So you can compare these search algorithms. Say for example, linear search, it takes n steps, and binary log 2 n steps. We can clearly see that the difference between these two computation. Binary search is about as fast as you can get. Yes, it is kind of a faster algorithm when compared to the basic linear search. And when it comes to sorting, bubble sorting takes n square steps, and insertion sort, it also takes n square steps. And there are other more efficient sorting techniques are available. And yes, we have just seen the basic sorting and searching algorithms and their complexity. So as we build these algorithms, in fact these algorithms are established a long time ago, and still people are working out to come up with a better algorithm, more efficient one for even for sorting as well as for searching. And as you come across these algorithms, one of the primary factor that is involved in any algorithm is that the number of steps involved. In other words, the computational complexity. We call it as computational complexity. That is one factor. The second factor is the time complexity. So we should make this as the constraint while developing algorithm, so that both are kept at the minimum level. Yes, the principle is the fastest or the heap sort, quick sort, merge sort. These are other sorts of algorithm, other sorting algorithms that are available. You can have a look at these algorithms as well. How does one measures algorithm? So we can take we can time how long does it take a computer to compute it. What if the computer is doing other things? Well, you know that whenever you operate a computer, there are a lot of different applications running, or different programs are running the back end. Apart from your operating system, you do have other simple things running around. So what happens if you get a faster computer? Well, we do have faster machines, but here this one is not that faster. Today's computer is much faster than the 3 GHz Windows machine. Let's say you have a better machine, and let's say how long does it take to measure this kind of algorithms in one such machines. Different CPU will require different amount of machine instruction for the same algorithm. That's true. So that's one of the thing that people have to note. For example, whenever you want to compare your algorithms, for example, an algorithm has been established in say 1990s, and they have run the simulation using some computers to compute the computation complexity as well as the time complexity. But if you are comparing the same algorithm today in your computer, like in today's time, of course computers are much faster than 1990s. So this comparison is not even, I would say. Definitely today's machine works much faster than 1990s, even 2000s, right? It's much faster than the computer that was available in say 2005 or 2010. Yes, different CPU will require different amount of machine instructions. So we have to be fair, and in fact we have to be very careful in measuring the algorithms. You can't just measure an algorithm based on just machine based. As I told you, the algorithm that works in a machine in 2010 would have a different computation complexity as well as time complexity when compared to the same algorithm that runs on a machine in 2020. Yeah, they have a different output. So we should be cautious of evaluating an algorithm. So that's one of the important factor. Of course, we do know that the worst case scenario, the operations that are involved, is one of the prime factor. So we can loosely define a step as a single computer operation. Well, that's a good way to start with in comparing or measuring an algorithm. A comparison, an assessment, or an evaluation for the given algorithm, regardless of how many machine instructions it translates into. Let's just say a step is a single computer operation. So let's now put these algorithms in the broad category of efficientness. Let's see how efficient these algorithms are, or in other words, how do we measure these effectiveness or efficientness of these algorithms. An efficient algorithm on a slower computer will always beat an inefficient algorithm on a faster computer. Well, that's seem to be quite obvious statement when we talk about algorithms. Okay, so this is in fact side inequalities. If you have an inequalities, you need to show, say for example, x is less than y, and you can replace the lesser side with something greater, say x plus 1 less than y. So this is simple measure. If we can still show this to be true, then the original inequality is true, right? If x plus 1 is less than y, then definitely x should be less than y. So that's kind of an inequality based information. Let's consider showing that 15 is less than 20. Well, do you consider this one? You can replace 15 with 16 and then show that 16 is less than 20. If you could show that, then definitely then 15 has to be less than 16 and 16 has to be less than 20, then 15 has to be less than 20. That's because we have this simple inequalities defined, and that's how we can simply define it. If you have an inequality, you want to show the same idea, you can replace something lesser. Like if you want to do the same, it's kind of complementary operation that we have just seen in the previous slides, where x is less than y and x is less than y minus 1. So you can have the same thought in if you still want to show it to be true, then you can use something like that. 15 is less than 20. Again, you can replace 20 with 19, then show that 15 is less than 19, because we know that 15 is less than 19 and 19 is in fact less than 20, then 15 is less than 20. Yes, that's quite a relation. And if you think from the proof point of view, in fact you can see how simple operation like because and then are used. In other words, it's like if 15 is less than 19 and 19 is less than 20, then 15 is less than 20. In other words, it's like if 15 is less than 20 and 19 is less than 20, this implies that 15 is less than 20. Can you get the things that we have seen earlier? It's like as if P is true and Q is true, then P implies Q is true, something like that. You are developing a logical relationship and you are seeing how this can be related to this inequalities that we are discussing right here, right now. Let's have more thought on it. What if you do such replacement and can't show anything? In the last two slides we saw some simple examples, but in fact there you showed the proof. So sometimes you can't able to show the original inequalities are true. Say for example you have 15 is less than 20 and you can replace 20 with 10, but you can't show that 15 is less than 10. In that case, yeah, so you can't say anything one way or other about the original inequalities. The original inequality is there, and if you want a strong basis to justify the trueness of the original equality, you should have a strong basis to show it. But in this example, since we have chosen or replaced 20 with 10, we can't say anything about the original inequalities. Let's review for the last time. So what are the things that you have seen? We talked about searches. That's the linear search which has n steps, and binary search that has log base 2 n steps. Binary search is about as fast as you can get, and sorting, bubble sort has n square steps. In fact, the insertion sort also has n square steps, and there are other more efficient sorting mechanism like merge sort, quick sort, heap sort, and so on. And these takes n times log base 2 n step. So in practice, quicksort is the fastest, although it is not guaranteed, followed by merge sort. And in fact, I encourage you to look at all those sorting mechanism, though we just consider bubble and insertion sort in this course. The big O notation. So it's one of the things that you will come across from now on. Let's talk about that. Let B of x is the bubble sort algorithm, and say B of x is O n square. We read B of x is big O n square. Yes, that's a big O. This means that the input size increases, the runtime of the bubble sort will increase proportionally to the square of the input size. Got it? So it means that the input size increases. If the input size increases, the number of, the running time of the bubble sort will also increase proportionally. Two are proportional to one another. Number of input as well as the runtime, proportional to the square of the input size. Yes. So n is the numbers where they have. So the constant, we have the n square. Let Lx be the linear or sequential search algorithm. We say that Lx is O of n, which means runtime of the linear search increases directly proportional to input size. So n is the input size and the runtime directly proportional to this input size in case of linear sequential search algorithms. Whereas in bubble sort, the input size increases, the runtime of this bubble sort increases proportional to the square of the input size. We know that the complexity we already discussed is n square step. It's kind of a big O operations. Big O notation, let's see, B of x is big O n square. Yes, B of x runtime is less than or equal to some constant times n square. L of x is big O n, which is L of x runtime is less than or equal to some constant n times. Right. So the worst cases for B of x is big O n square. The worst cases, the constant time is n square, whereas L of x, the big O n is, the worst case is the constant time n. Let's look at this simple proof. Here f of x is x square plus 2x plus 1 is big O x square, and in other words we say x square plus 2x plus 1 is less than or equal to c times x square, where c is some constant and for input size greater than some x. We know that 2x square is greater than 2x whenever x is greater than 1, right. So there you have x square is greater than 1 whenever x is greater than 1. So we will replace 2x plus 1 with 3x square. So you can see the whole relation, because we have come up with this thought with x square plus 3x square equal to 4x square, because originally in this problem that we have is we had x square plus 2x plus 1, and now we are replacing 2x plus 1 with 3x square, because we do have a relationship in which we come to know that 2x square is greater than 2x when x is greater than 1, and x square is greater than 1 when x is greater than 1. So with this thought we have a relationship from 2x 1, we have this thought of 2x square and x square. So that's where 2x square and x square takes us to 3x square. and this yields 4x square is less than or equal to c times x square. This for the input size 1 or greater when the constant is 4 or greater. So the thing is you should know that the constant c there should be 4 or greater than 4. That is how we come to know that f of x is big O x square. Let us look at this examples here. The big O proof, where you have the function for x squared plus 2x plus 1 and big O x square is given to us, and it is kind of a linear increase in this linear line. Let us look at this big O problem here again. If you look at this, x squared plus 1000 is big O x square. We know that x square is greater than 1000 whenever x is greater than 31. So we replace x square with, we replace 1000 with x square. So then you have 2x square is less than or equal to c times x square. C is the constant, so c can be either 2 or greater than 2. So c is greater than or equal to 2. So again, similar thought for a different issue. Again, you can replace 7 with x, and 4x is less than or equal to c. Again, the c would be greater than or equal to 4. In general speaking, the big O issue is like it's kind of a O of x we have seen here is the operation. In other words, people use the term big O as the operations involved. So here again 3x plus 7 is big O x square, and when you try to solve this the whole stuff, you get the same or similar results. So this is also true for x is greater than 7 when c is greater than or equal to 1, or you can see in fact it also works this way, because here it is not 4x square less than or equal to c times x square, it is 4x. So that is why it would work for c is greater than or equal to 1. So if function is O of big O of x, then it is also big O of x square, it is also big O of x cube, meaning big O of x function will grow at a slower or equal rate of x, x square and x cube. Is kind of exponential part that they have here, and the functional growth rate, if the input size is 1000, big O of 1 is 1, and log of big O of log n is 10, big O of n is 10 power 3, big O of n log n is 10 power 4, big O of n square is 10 power 6, big O of n cube is 10 power 9, n power 4 is 10 power 12, and that's it. Big O of n power c is 10 power 3, that is 10 power 3 times c, c is the constants there. 2 power n is 10 power 301, that is huge. N factorial is 10 power 2568, n power n is 10 power 3000. The many interesting problem falls into this category, so that is huge amount. We do not want to play with that right now, so let us let it, of course we can find some proofs for that in fact. So here is a simple graph that displays as gives us this complexity functional growth rate information where we can find some big O estimates of elements for n factorial, 2 power n, n square, n log n, and so on. Yeah, that is the logarithmic scale that is given to us there. Integer factorization, factoring a composite number into its component prime, that is big O of 2 power n, where n is the number of bits in the number, and we have, if suppose we choose 2048 bits as a RSA key. If you remember RSA crypto graphic part that we have seen, it takes 2 power 2048 steps. That's quite a large, right? So it takes 10 power 617 steps to compute. A similar thought of let f and g be the function. We say f of x is big O of g of x if there are constant c and k such that the function f of x is less than or equal to c g of x, where x is greater than k. So here we are looking at the function part where we have function f and g, and with respect to the big O issue of problem concerning the operations. So for g of cx, f of gx, we have the functional growth given with respect to the big O definitions that we are discussing. So finally, a note on this big O notation. So assume that the function f of x is big O g of x. It is sometimes written as f of x equals big O g of x. So this is with respect to the big O operations that we are talking about. And in this class we will write f of x is g of x. That's what we have been discussing. And if you relate this with that of composite function f of g of x, g of f of x that we have discussed in the past, you will see actual part, because we talked about functions in the past, and in which we talked about composite function in which we have f of g of x, g of f of x, and again that involves the big O, or in other words the computational complexity of such functions. Generally speaking, today we just talked about some basic thought about big O notation. Not only that, we saw examples of bubble sort and insertion sort, and we talked about the complexities involved in an algorithm. Whenever we talk about algorithms, the complexity is something that we have to deal with. We should be careful about having too complex algorithms that takes too much time and too much computation complexity. We don't want that. We want some algorithms that are quite simple, and it can perform tasks in a limited number of time with limited complexity. In other words, the number of steps that an algorithm takes to complete should be as less as possible. We don't want an exponential growth, but there are no other choice right now but to have these different algorithms that has higher complexity. We are still working out. There are a lot of research going on in reducing such complexities involved in our algorithms. So that's why the efficient algorithms are still being developed. So as we move ahead, I look forward that you guys can work out on different algorithms and try to solve it, try to program these algorithms and see whether you could able to input certain values and get a desired output. Why don't you try this out? I am looking forward to see you in the next lecture. Until then, have a good time and goodbye.